an Icom IC 706 MK2G with PLL unlock condition. So what's going on here? Welcome to TRX Bench. Yeah, you can see I'm already here full in the troubleshooting procedure. As this radio came in with no receive indication, and well, I thought that might be one of these boring faults, and I thought it is not really interesting to share. But then when I started here our troubleshooting, I recognized that yeah, it is more than a boring fault. It is really a PLL problem here on our PLL board, and what you are looking at here is already our PLL board. And as I said, I already started here our troubleshooting, and what I've done first, I just put in here my test ribbon cable, this both here, because this ribbon cable are really known for making a lot of trouble. And so I thought, let me first put this ribbon cable in to be sure that everything is fine. But that was not finally the solution. We still have a problem. The radio does not receive, and so next step, or together with placing here the new ribbon cable, or the test ribbon cable, finally, I have already taken this shielding here from our ICs down here, so we come in a bit to what these both ICs are doing. But first of all, let me show what the radio does or not does. Okay, so when we switch it on, like so, you see it is initializing and booting up the MCU, and we have display and everything looks fine. But what we directly recognize, so there is no static, there is no noise in the speaker, and that is always an indication for is our PLL circuit running good, or are all VCOs working fine. So, you know, that is always an indication that there might be something wrong with the PLL. And we have seen it with the Yaesu FT857. If there the PLL is unlocked, we have the blinking display. The Icom is not doing it, but what I've done first, I've checked if the radio is in unlock condition, and that can be checked with a simple voltage check at the unlock indicator transistor, and I've seen that the radio really is unlocked. Okay, but now step by step. Okay, and this is a block diagram of our PLL circuit, and what I'm doing first, always when I guess there might be something wrong with the PLL, I simply look for the unlock condition, and you can find it here. So here is our unlock indicator. So this is here called a level converter, but it is not more than a simple transistor which is giving a high or a low to the MCU, so to the microprocessor. And you see that we have here two unlock passes, which comes here from this PLL IC, and here is another PLL IC, and they can give unlock condition, and then the level converter gives this unlock towards our MCU, and then the MCU is shutting down, for instance, the audio circuit. So the MCU is simply muting the audio circuit, and that is what we have recognized first, so that there is no noise, and that could always be an indication for an unlock condition. And therefore that was the first I've done. I've checked here for unlock. And when we go right here into the schematic, you find here our ULP and ULD. So this is the line which is coming from our both PLL circuits, and we talk about that in a bit. And you see here, so that is a so-called level converter, but it is nothing else than if the radio is in lock condition, we have here a high, and high means that it is 8 volt, and 8 volt is reported to the MCU, and the MCU knows, oh okay, PLL is just fine, so we can run the radio. But if there is an upcoming unlock, regardless from where it is coming, then this level converter turns to low, and the MCU knows, oh, there is something wrong with our PLL circuit, and well, that means the radio will not work, so we shut down different circuits. And one is that the MCU is muting the radio, and we have seen it with, for instance, our Yaesu FT857. There we have seen that we have this blinking display, which is indicating directly that there is an unlock condition. Here we need to go to this test point, and we need to see if we have a high or a low, and if we find here a low, then we know, okay, that is an unlock. And then if we find this here, we can check if there is here a high, because we need a high to this level converter to switch it to low. So we need here a high, which means that there is from one or the other line coming an unlock. Okay, and in circuit we can find our level converter down there. Okay, so let me zoom in a little bit more that you get an idea. And let me see that we still have it in focus. It's a little bit difficult here with the lightning, as you can see, but anyways, it is this little transistor here, and at its collector we can pick here our signal for having lock or unlock condition, and we need a low, so that means only a few millivolt maybe. Then we know it is low, and this package here is our dual diode package, and if of one side we have a high, so approximately 5 volt, I don't know exactly, we know that there is an unlock, and that is what we want to check right now. Okay, so let me first go down to the diode pack, where we have the both diodes, and if there is an unlock, then we should see an high, which is approximately 5 volt. So let me go down to this package here. Yeah, 5 volt, so that is indicating we definitely have an unlock. And now let me go to the collector of our level converter, so-called level converter, and let's see what we have there. Hang on a second here. Here it is, and you see it is not changing. Yeah, it is only a few millivolts, as you can see, and that is our low. What I told you before, that is our low, what we have when we touch the collector. And we have here our approximately 8 volt, which is at the resistor. I show it in a second in the schematic. So that is the supply voltage to this level converter. So now we are really sure that it is in unlock condition. Okay, and you see here our level converter, and it is nothing else than a digital transistor. Digital transistor always means so there are some resistors inside as well, and you may see that as long we have here no switching voltage, this resistor is not turned on. And if it is not turned on, we have here an high, so approximately our 8 volt. Okay, and if it gets turned on by a high coming here from one of these lines, then it will switch through, and we will have here at this point 0, and that 0 is then our UL indication towards our MCU. And when we test here, of course, we have here our approximately 8 volt, which we have seen, and at this point we have a low, which means that this transistor here is turned on. So that is the whole magic here. Okay, back here into our on our PCB. Before we go and discuss what our next step might be, I want to show you that what I found here, and you may already see that obviously somebody was already in. And you see, yeah, that is very, very unprofessional. And when you look here from the side to these resistors, you see that there is a gap under the resistor, which means that it is not completely lying here on the surface. And that all is telling me that somebody was in and was not really able to handle SMD technique. I don't know why somebody already was in, so maybe that somebody else earlier has already done a repair attempt, or I don't know, but it is very, very obvious that somebody already was in. Okay, time to discuss how we can go ahead and how to troubleshoot a PLL circuit. So this here is the architecture of our PLL circuit, and well, you see that what we always need if we have radios like this, we need our different local oscillators. So in this case, our first LO, our second LO, and this is called BFO for the SSB, or it is a third LO for FM. So this LOs needs to get produced in our PLL unit to bring the frequencies to our intermediate frequencies, which we need to convert our incoming signal here from the antenna finally back into an audio signal, right? And therefore, of course, we have our PLL circuit, and the PLL circuit itself always relies on a reference oscillator. So our reference oscillator is standard, and you see it should be in this radio at 30 megahertz. And so this 30 megahertz really should be rock solid, and therefore you find in many radios, many better radios, minimum TCXO, so a voltage controlled oscillator, or maybe you find as well oven oscillator, so that this is really a good and rock solid frequency. And so the whole radio simply relies on this standard. If this standard is bad, then you know all your frequencies are bad as well, so you're never really on frequency. So that is here really key. Okay, and then it is all working with VCOs. So you see here we have 1, 2, 3 VCOs in our main loop PLL, and we have one VCO in our ref loop PLL, right? And the idea of a PLL circuit is always the same, and it is very simple. PLL is standing for phase lock loop, and well, that is what is really happening here. So there is always a so-called phase detector, and the phase detector is simply comparing two frequencies, and that is first of all a kind of reference frequency. And you see, I will explain it later. So we have here a DDS, which relies on our reference oscillator, right? So that means whatever comes out here out of our DDS is a reference frequency. And this reference frequency gets compared by the feedback of our voltage controlled oscillator, in this case here our Q1. And first of all, VCO is let me call it a free running oscillator, and that means it is not stable, so it will move, and it depends on the temperature or on the aging of the components which are used here in this free running oscillator, so it is definitely not stable. But when we get or feed back the output from our voltage controlled oscillator back to a phase detector, right, and we compare the output frequency and our reference frequency, we can simply create a tuning voltage, and that is finally the output of out of a phase detector, right? So we can create a tuning voltage where we can then adjust our VCO with. And that means if this phase detector is seeing a phase difference between our reference frequency and the feedback frequency, we can adjust finally our running oscillator to the right output frequency, that both are in phase, so the reference and the feedback, and then the phase detector can lock, and we have a rock solid output frequency from our VCO. Okay, so that is finally always the same. And you already can see this 30 megahertz is converted here to 10.665 up to 10.683 megacycles. So that is a needed frequency for our main loop PLL. And what you can see here, so we have divider here and we have divider here, and this divider are necessary to adjust the different frequencies, because this VCO should not run on only one frequency, so we need really a bunch of frequencies to operate our radio, because here our first mixer gets all the different frequencies, and you see it is not only our shortwave band, it is also our VHF and our UHF frequencies, and all these incoming frequencies needs to get converted to our intermediate frequencies, which is here sitting on 69.0115 megacycles, right? And that means we need different LO frequencies simply due to the fact that we need to create always this intermediate frequency, because this intermediate frequency is what we want to use for any further conversions that we finally get back to our audio, because the audio, the speech is, or maybe the music, so for broadcast radios, because every radio is working in the same manner. So therefore our goal is always to win back our audio, and that is why we convert it. And well, I do not want to go too deep into the mixing and why we convert it, and not only one times, but more than one time. So that is the radio theory, why we do that. But we are talking right now simply about our PLL unit, and how our PLL unit is creating the different local oscillators. And you see, for getting our first LO is the most complex job our PLL circuit has to do. For the second LO, so that is a fixed LO, in our case here it is 60 megahertz, which is simply twice our reference frequency, and yeah, so that is simply a doubler circuit and a bandpass filter, and then we have here our 60 megahertz, and our third LO, or our BFO, is also sitting on one frequency, and therefore Icom has used here a DDS as well, which also relies on our reference oscillator frequency, and therefore these both LOs are relatively simple to create, but our first LO is the most difficult part, because remember, when we tune, we really want to go down into the hertz area. So it is not only steps of 1 kilohertz, for instance. We are moving over the band with our main frequency dial. So we just want to have smaller steps, maybe 100 hertz or 10 hertz or even 1 hertz, and then it is really you know, that is really a job to be able to go down to this fine resolution, right? But that is not what we want to discuss today. I mean, therefore we need to know about the theory here behind these dividers and how it all works together. Today we just want to look for a practical way to check if these circuits are working or not, and therefore it is important to know that we always have finally a reference frequency and a feedback frequency, and this both needs to be the same, and we have here exactly the same, so simply forget the divider in between, so that would be another story. But here is a phase detector as well, and you see we have here our reference frequency, which is coming here from our ref loop PLL, so that's the reason why it is called reference loop PLL, because this input is reference frequency, and then you see the feedback, which comes here simply from our voltage controlled oscillators, and this both frequencies get compared in our phase detector, and we will get here at the output of our phase detector an up signal or a down signal, depending on where our VCO is sitting, and together with the loop filter we have a nice DC voltage, which then can influence our VCO. And now you maybe understand it a little bit more why it is called VCO, voltage controlled oscillator, and that is what the PLL is doing. So together with the loop filter, it is creating a nice voltage for the VCO to tune finally the frequency to exactly what we need this frequency. So that is what it is all about, and we can test it simply by seeing if the VCO is working. So that is the first what we can check, and secondly we can check if the reference oscillator is present, and in this case, because this 30 megahertz needs to be converted into this 10 something megahertz, and therefore we have a DDS, and the DDS is nothing else than direct digital synthesis, and that means that on a digital way we create our, in our case, sine to have finally the right frequency here at our phase detector, and therefore we have special DDS ICs, and here we have as well a DDS IC for our BFO, right? And yeah, so therefore we get datas, or we need the datas coming from our MCU telling the DDS which frequency and of course what kind of waveform, a sine or a ramp or a square or whatever. So everything can be created by a DDS, and the respective software to have the right code to create the needed signal, and all is done digitally, right? And yeah, let's now go here into our circuit and check if we can find here some of our frequencies. Okay, so don't get confused, just a short look here into our schematic. So this IC 101 is our ref loop PLL, and that is a PLL IC together with DDS IC. So both is here inside this IC, and yeah, we find all the inputs which we have discussed before. So this, for instance, here is coming here from our ref oscillator. So that means we should be able to read here our 30 megahertz, right? And up here, this here, all around our Q1 is our ref loop VCO. And we should find here an output frequency around 10 point something megahertz, okay? And this frequency will be feedback here. Let me see that I find the right way to this little amplifier. And this amplifier will then give this feedback frequency to the input of our ref loop PLL. And on the other hand, we have seen it on the diagram that we have a DDS. And the DDS you can always find, or you know that you have maybe a DDS in the circuit if you see a resistance network like this here, because that is nothing else than the digital analog converter. And you see here is the output, and you find here a filter, and this filter is sitting on, let me see, this filter here is sitting on approximately, again, our 10.6 something megacycles, and then we have here our little amplifier, and that is our ref frequency, and that is, as you can see here, feed into our PLL IC, which is our ref frequency. And yeah, now it is very simple. This ref frequency gets compared with this feedback frequency from our little VCO, right? And the output of our PLL IC, we have already said, is the up or down signal, and this comes out here and goes to our input of our VCO. And you find here a little varactor diode, so that is a cap diode, and you see here a coil and a capacitor in parallel, so that is always the indication that we have a kind of oscillator here, and the oscillator frequency can be influenced if we have simply sitting here a diode, a cup diode in parallel. And a cup diode, as you might know, can be changed in capacity by simply putting a DC voltage onto it, right? And then this capacity is changing, and if this capacity is changing, then we change simply our VCO frequency, right? And that is all what it is about. So we get here our up pulses into this loop filter. So loop filter is this resistor, and this capacity here. Okay, and then we have a nice DC, and the DC will influence our capacity, which will then influence our VCO frequency. Okay, so basically very simple. And now let's go down to our circuit and let's probe. Okay, and this here is our IC101. So that is a ref loop PLL circuit with the integrated DDS and the digital analog Wandler, so converter, our digital analog converter. So our resistor network we have seen in the schematic is under this additional shielding. Okay, and this here is our IC901, so that is a BFO DDS, and you can see here a bunch of resistors which are finally our resistor network for digital analog converting. And our VCO, or all our VCOs, are behind these shieldings here. So it is the tin here is all over it, so that nothing can influence our oscillators, which are in here. So we have here in this down here our ref loop VCO, and in this here we have our main loop VCOs, and in here, so this is our reference. So I have opened it so that you can have a look inside, and what you see, what a wonder, we can find our crystal here, and that is our 30 megahertz reference crystal. And very easy basically, so nothing special. So we put it back over it so that it is nicely shielded, and now we really can go down and test. And if we look down here, we find here a transistor, and we find, let me see that you can see it, and you can find here a transistor, and up here, and this transistor, for instance, is the Q161. And remember, when we have seen our schematic, we know that this here is our little amplifier for our 30 megahertz. So that is the reference frequency coming from our reference crystal we have just seen. And then down here we have finally the let me double check. So we have the Q71, which is this. I have to go down, of course, otherwise you don't see nothing. And this here is our Q71, and the Q71 is the amplifier for our VCO output. And then of course we have here our Q what is it called, 51. So this is here Q51, and that is a little amplifier for our DDS output. And this both frequencies gets compared, and then the IC itself will give out an up or down signal for adjusting finally the VCO, which is sitting, as I already said, down here, here in this tin it is sitting. Okay, and we have now our scope screen, and the first what we check is our reference frequency, our 30 megacycle at our Q161. So let me go down to the collector, and here it is. So we have a nice 30 megacycle sign, and you can see it up here, and it is our 30 megahertz reference frequency. So that is telling us that our IC 101 is really getting the reference frequency. So that means our reference oscillator is working, no problem. And now let's see if our VCO is working, and therefore I go down to Q51. Let me go down to Q51, which is somewhere here, and yeah, you see again the frequency is 10.6 something, and that is the frequency from our ref loop VCO. So you see that is working, and it is present at our IC 101. And now of course we need our DDS output, which is the frequency which should also sit somewhere around 10 megacycles, because these both frequencies are the frequencies which gets or should get compared to get the right tuning voltage, right? So let me go down to our Q71, which is the little amplifier from our digital analog converter, and I go down now to the collector and checking the frequency here, and you see that it is going up and down, but we have no output, so we have no DDS signals, no reference output from our DDS portion of the IC 101. So that is not good news. It is completely missing here. Okay, now we know that here the DDS reference frequency is missing for any reason, so we do not know yet. Maybe it is faulty, or maybe that this here has given an unlock indication. So we should check here our BFO frequency, which should sit on 9.01 megacycles. You see here is the output. So this is the BFO output here from our DDS IC. And let's simply check if we have our 9 megacycles here. So this is here the filter circuit, and yeah, as I said, here we should be able to probe our 9 something megacycles. Okay, and back here to the scope, and I'm now here down at the output of our DDS IC for the BFO, and there is nothing. So let me show you what I'm doing here. So I'm here with my probe directly at the output behind the filter. So this here is the filter. So let me check if we can go here somewhere to our filter set. Let me see here somewhere. Is there something? No, nothing. So absolutely nothing at all. So it looks like that this DDS IC is not working as well. So that is no good news. Yeah, and that is the IC 901. So that is our BFO DDS IC, which we have tested before. And again, you can also see here the resistor network, and then this here is our output, and we should have here 9 point something megacycles. So let me zoom out a little bit here, that you get a better overview. So here, that is our IC 101, where we have seen that here our 30 megahertz were just fine, but here the output from our DDS portion of this circuit was not present. And now we have tested here the same. So let me see. Here you see the BFO output, and that is where we have tested, and we have tested here at the filter, but we simply had no output here from this DDS IC as well. So therefore, next step, let's see if we get our voltages, that all the supply voltages are present for getting this ICs finally operated. Yeah, and what are we going to do? So very simple. Let me enlarge it here a little bit. So I just want to see if we have here our 5 volt supply voltage present at our IC, and of course I want to check here from our IC 101 as well our supply voltage, which comes here over the L131 and will then supply here our IC 101. So that is now our next step. Okay, on the PCB we have this little coil here, or choke or whatever, which is feeding or over this L, our 5 volt is gets feed here to this DDS IC, and then we have here the coil. Let me see. Okay, now you can see it, and we have this coil, which is over this coil this IC gets its supply voltage. So let's check if our supply voltage is present. Okay, so let's start here. So probe is already down, and our meter is reading 5 volt. So fine, no problem. And let's check the voltage, of course, behind our filter, or L or whatever, because that is of course important, because if something is wrong with our IC, then very often this little L's get simply destroyed. So now I'm probing here behind our L, and let's see what we read. Yeah, and there is nothing. So that means obviously that this little L is destroyed. If we are lucky, it is only this little L which needs to get replaced, but that we will see in a second, because now I just want to go over here to our IC 101 and let's check what we have here. So here's our input, and there again we have our 5 volt, very nice. And now we go to the other side and let's check there. Voltage, oh look here, that is funny. So we only see 3.3 volt at the other side of this little coil, and yeah, that is indicating that either the IC down here, so our IC 101 is drawing a lot of current, or something is wrong here with our coil. But anyway, either way, both is not really a good sign, because both could mean that there is definitely a problem with this IC as well. Okay, so I've switched off the radio and it is completely disconnected from the power supply, and the meter is set to continuity, so that means we have here our ground pin, and of course if I go now to a ground point we hear the beep, so that is normal. And let me see if we can get it a little bit better, light here, so maybe so. And of course if I touch here this ground, we have our beep, because there is continuity of course between here my ground clip and now this ground shield here. And well, if we are lucky, then this little coil gets destroyed by I don't know. If we are lucky, nothing has really happened to our IC, but it might be that there is a short, and therefore let's see what we have when we go here to our supply line. Yeah, and that is a dead short. That is really bad news. I mean, we can be lucky. We can be lucky that one of these little caps has a dead short to ground, so that would be the better outcome. But most of the time it is the IC itself, and remember this coil is open, so therefore if we go here to this supply line, so this is the plus 5 volt supply line, and this is directly shorted to ground, and most likely directly here over the IC. So that is 90% that this IC is dead. If we are lucky, as I said, one of these little caps is dead, but most of the time it is this. And then let's see what we have here, because we have seen that we really had only 3 volt, which is indicating that this IC might draw a lot of current. So let me go down here. but you do not hear a beep. And on the display I see we have over 700 ohms, and that is not bad, so that is good, but it is not finally telling us that this IC is fine. So this IC still could be bad, so we do not really know it. So what can we do to get a better idea if there is something wrong here with our IC? I mean, we have seen it is a dead short, and if we have a dead short, we simply push power through this IC to see if this IC is dead short or not. Okay, and what I said is that we have disconnected our radio completely from the power supply, so there is definitely no voltage coming from the power supply, but I have now here set this power supply to 4 volt, and I've set maximum output amps to 1 amp. I can now switch it on, and now what I can do, we know that, do it this way. So what we definitely know is that this little coil is dead, so it is open, and if I go now behind our coil, then I'm feeding the IC, okay, and I've set the voltage to 4 volt, and we know that normally it is a 5 volt IC, and if I put 4 volt to this point, nothing should happen to the IC, and therefore if it is fine I can't destroy it, but if it is bad we will definitely see a huge power which gets drawn, and then we should easily be able to identify what's really going on. And therefore, yeah, I'm gonna put it down here, and I already see my amp meter, so let me go here to the power supply, and yeah, let me go down here to the coil, and let's feed the IC with our 4 volt, and now I'm at the feed point, and you see the IC is directly, or maybe the cap is directly drawing 1 amp, and that is not a good sign. But I wanna let this 1 amp run through the circuit, because I want to identify is the IC the problem, or maybe the little caps around. And therefore, once again, I put here my probe down to the feed line, and now we have 1 amps, and I'm simply testing here the temperature with my finger, and I can say you it is getting hot. Yeah, definitely this IC is getting hot, and that means that the current is flowing through the IC and not through one of these little caps, because if the current would flow through the caps, which could have a short as well, then the IC wouldn't get hot, but the IC gets hot, and that is telling me, unfortunately, this IC is definitely dead. But I'm interested what's happening if I do here exactly the same with my, I need to put down here my ground from my test power supply, and I just want to do the same. So again, it's a 5-volt IC, and now when I put it down here, I should see something, and yeah, that is looking much better. So let me show you what I see. So feeding it with 4 volt, now I'm at the feed point, and you see we are only drawing 46 milliamps, which is not too bad, and yeah, we have a little chance that this IC might be fine, but we can not finally tell if it is true or not. So we don't know. It is not getting hot. I mean, 41 milliamps could be really the operation current. I'm not entirely sure, as I do not have a data sheet. So that is a real advantage of Icom radios. So you very often simply do not get the data sheets because these are Icom customized ICs. So hopeless. But it's not getting hot. So it could mean that this IC is fine. I'm still feeding my 4 volt and everything is good. But anyways, we know this IC is definitely dead. Yeah, next step will be I have to take out the complete PLL board, and yeah, then we will have a closer look to the PLL board, and then we decide how to go ahead. Okay, and our board is out, and yeah, I'm still very unhappy with the situation that somebody has already done some repair attempt to this radio, and yeah, therefore it is not really easy to decide if it makes sense to fix this board, as you know, you never know if yeah, there are some additional surprises if we have, for instance, replaced this IC. So that is difficult to say, because what has this person who has done this, what has he done in general to this board or to the radio? So we really don't know, and this yeah, you know, is always a nightmare if you had a golden screwdriver in. So not really know. I really don't know what we should do, because you know, this IC and this IC is not really cheap, so both ICs are expensive, and if we have changed for instance this ICs, and then we have some additional surprises, then this repair really becomes very expensive. And you know, it is always difficult to say, does it make sense to go ahead this way, or maybe is it better to look out for a complete new board? It is not that this board can't be fixed, but it is a question of the price, what you know, the owner is willing to pay for these components, and yeah, if it is then working, it is fine. But if we have additional surprises, then we are really at a point what is not fun, you know. Yeah, anyways, let me first of all test this coil, because we have seen we have a drop here at this coil, and therefore I'm really interested what is the resistance of this coil. And the resistance is, funny enough, 100 ohm. And that is the reason why we had the voltage drop over this coil. And we all know that a coil normally has a very low resistor. So for instance, if we check this one here, because we know this here is working fine, and this has 2.6 ohm resistance, and that I would say is a typical resistance for a coil like this. But to have 100 ohm is different. So that means that yeah, something must have been happened to this IC as well. So it is difficult to say if it is working. I mean that we didn't see the DDS output here, so that was what we have seen. Could be the reason this IC is dead, and we have an unlock condition to the MCU, and as I said right at the beginning, the MCU is then shutting down different operations. So maybe because this is dead, this has been shut down in a way. So not easy to say. So we should need to replace this IC to see what's going on here. And if it is still not working, then we have a problem here as well. And we are again at the beginning of our story. Well, nice story. Okay, before we take off this IC, I just want to see how our component would react. Let me see if we can get it here into view. Yeah, I think you can see here. Yeah, that is the IC. And what I'm interested is, I'm not sure if I can get it on camera, but I try my best. So yeah, this is here a reflection from this can here. Okay, so that is not a heat indication. Yeah, you see my hand, that is definitely a heat indication. But I just want to feed my 4 volt, and now it is drawing that current, and I want to know what's happening. And what we can see so far is that the IC is getting hot, and yeah, it is obviously not yeah, it is completely hot. It is completely hot, and I cannot see that some of this capacities is showing any heat indication. So I am 99% sure that it has really something to do with the IC itself. Okay, so we remove the IC to see if it is really the IC or is it something different. So therefore I put flux here around our pins, and yeah, I'm excited if it is really the IC, but as we have seen, we were not able to identify with our camera any problem. So let's see. Okay, our hot air needs to get up, and I guess I put a bit more. Okay, a bit more air, and let's wait until we have the right temperature, and we start in a respective distance, not to shock here the board. So very carefully heat up the board itself before we go down and try to lift the IC off here our PCB. Don't know if you can all see. I hope. It's a little bit difficult. Okay, let's see. Still heating the board, trying not to destroy anything. I mean, that is always the risk. Okay, let's see. Hope that the board temperature is now okay, that we really can go down. I do not want to make it too hot, so better to be careful. Okay. Here we are. All right. Yeah, here is our ship, and all pads are there, so nothing is wrong. Very nice. Okay, not cleaned yet, but I think you can see that all pads are there, and that is very, very important. And of course we are interested if the high current drone is now over after we have lifted off the IC. So therefore of course I go down here to can you see it? I hope it is all a little bit difficult here. So I go down here to our little come on, to our little coil. So I'm down at the coil, and you see, yeah, all is just fine. So I take it away, so 0, and it is pulling 7 milliamps, and that is just fine. I mean, there are resistors and what have we around here, and therefore that is definitely fine. We have really a dead IC, and yeah, that needs to be replaced. But anyway, as I said before, we still have another problem, as we do not know what's really going on here, and therefore I have to discuss it with the owner. It is no easy decision, but anyways, I will stop the video here. I mean, it is long enough on one hand, and on the other hand, I do not know what the next step will be, but I think you get a good impression how you can troubleshoot a PLL circuit, DDS, PLL, VCO, and what have we. And yeah, if that was a bit interesting for you, then I definitely have reached my goal. So therefore, let me stop here. Let's take it as a tutorial, and I will discuss with the owner what we're gonna do. As I already said, it is not cheap, and the 706 is yeah, more or less an old radio, so therefore it really needs to get considered in all the different directions. So therefore, yeah, that's it for the day. Thank you for watching, and I hope it was a bit interesting for you. If you like it, please give me a big thumb up. Thank you, and catch you next time. Bye.